Math 1332, Chapter 10, Probability and Counting Techniques. Section 2, the Fundamental Counting Principle, Permutations. Video 2, the Fundamental Counting Principle, Repetitions versus No Repetitions. I'll explain what I mean by repetitions versus no repetitions in the first example, and I'll also illustrate a visual technique to help you implement the fundamental counting principle. It's nothing fancy. Here's the scenario. You want to set up a new passcode for your phone. A passcode consists of 6 digits which may be repeated. How many possible passcodes are there? Now, this may not seem like a fundamental counting principle problem like in the previous video when we were selecting options to make a meal, but it is, because every time you make a sequence of decisions and you know how many choices you have for each decision, you are doing the fundamental counting principle. One way to illustrate this is to draw a blank for each decision you have to make. In this case, I need to make 6 decisions. What's the first digit? What's the second digit? What's the third digit? The fourth digit, the fifth digit, and the 6th digit. And if you want to, you can label these first digit. In fact, let me pause and label them all real quick. Or I could just type them in. But if you set up one blank for each decision that you have to make, then in each blank, you can just write the number of choices you have for that decision. Now, let's be clear that when I say digits, I mean digits like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So in other words, for each blank, we have to choose a number from the set. 2, 3, 4, 5, 6, 7, 8, 9. So let's start with the first digit. How many choices do we have for the first digit? If you said 9, you are incorrect. Because when you count all the digits from 0 to 9 through 9, there are not 9 of them, there are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 digits in there. We have 10 choices for our first digit. Since we can repeat digits, in other words, let's say the first digit is 7. That means I can use 7 again for another digit. How many choices do I have for the second digit? 10. And for the third digit, 10. In fact, I have 10 choices for every digit. And if you notice, I subconsciously put a multiplication dot between the first two 10s. Let's just pretend for a second that I didn't. Come back, everybody. Nope. There we go. All right. The fundamental counting principle says to count the total number of ways to make all of my decisions, I multiply the number of choices for each decision that I have to make. So in other words, I multiply all these 10s. Well, 10 times 10 times 10 times 10 times 10 times 10 is 1 million passcodes. I'm not sure what just happened there. When I get too far to the side of my screen, some thing slides off from the edge, and I don't like it. All right, so we only have 1 million different possible passcodes. So, good luck just guessing the correct one at random unless you do something silly like put your 6-digit birthday. Don't do that. Don't do that. Birthdays are public information, or at least I think you can find them online. But let's change the question. What if you're not allowed to repeat a digit? Well, the setup would still look the same, so it would look something like this. All 6 digits that we have to make decisions for. But if we're not allowed to repeat a digit, that's going to change things. Not in the first decision. We still have 10 choices for the first digit. But let's say for a moment that we pick 7 and we put it in there. We pick 7, how many choices do we have for the second digit? It's not 10, because we can't choose that 7 anymore. It used to be 10, but we used up one of our choices, which means now we only have 9 choices for the next digit. Let's just say for the sake of discussion that the next digit was 0. How many choices do I have for the next digit? Well, there's only 8 digits left to choose from, and then 7, and then 6, and then 5. This will give us a smaller number, and I apologize for not having this answer in advance, but I can find it real fast. 151,200. Let me do that again just to make sure. 151,200. 151,200. So if you noticed, it cut it down by a lot. It cut it down by almost 85%. Ooh, fast math. It's not as bad. It's not as hard as it seems if you know enough tricks. But yeah, when you're doing the fundamental counting principle, if it's not clear if repetitions are allowed or not, then it should make it clear if repetitions are allowed or not. But if you see something that specifically says with repetitions or without repetitions, then they're really forcing you to focus on, well, the numbers change as we move down because the number of decisions gets lesser and lesser, or will they remain the same as we go across because the number of decisions remains the same. Let's take a look at another example. A combination lock can be opened by turning the dial to the correct 3 numbers in order. One direction, backward. Yeah, most of y'all know how a combination lock works. Combination lock. How many combinations are there if the numbers range from 0 to 59 inclusive and numbers can be repeated? I don't think in an actual combination lock the numbers can be repeated, but let's pretend that they can. How many decisions are we making? How many? Yeah, we're making 3 decisions. First number in the combination, second number in the third. I'm not saying we're setting the combination, we're just figuring out the total number of combinations. Well, how many choices do I have for the first number in my combination? How many numbers are there from 0 through 59? Did you say 59? You're wrong. There's actually 60. Because if you started counting with the number 1 through 59, that would be 59 numbers. 0 would make it 60. There are 60 numbers we have to choose from for the first number in this combination. And since we can repeat, then we still have 60 choices and 60 choices again. Pause to erase. 60 times 60 times 60, first off, ends in 3 zeros. So there'll be a comma before them. And I happen to know that 6 times 6 times 6 is 216. So only 216,000 possible combinations on your combination lock if the numbers can be repeated and the numbers on the combination lock are 0 through 59 inclusive. But what if numbers cannot be repeated, as most combination locks don't allow? Well, if numbers can't be repeated, then we still have 60 choices for the first number in the combination, but whatever number we pick, we can't use again, which means now we only have 59 choices for the next number, and then 58 as well. So what is 60 times 59 times 58? 205,320. 205,320. So you can see in this scenario, not allowing repeats didn't lower it by too much in terms of relative size. It only lowered it by 11,000. A little more than 10,000 out of 216,000. In the previous one, it cut it down from 1 million to 150,000 and lost over about 850,000. Now, why do I keep putting quotation marks around combination? That's foreshadowing. That's a cliffhanger. Don't worry, when the time is right, I will explain, and we will revisit this scenario. Let's try one more. How many ways can you arrange 8 distinct books on a shelf? So how many decisions do we have to make? Well, we have to decide what book to put first, what book to put second, and then third, and then fourth, and then fifth, sixth, seventh, and then eighth. And all the books are different. So how many choices do we have for the first book to put on the shelf? 8. Can we use that book again? No. This is an implied no repetition scenario, because once you put a book on the shelf, you can't choose it again to use at a different spot on the shelf. So if we have 8 choices for the first book, then we only have 7 for the next, and then 6, and then 5, and then 4, and then 3, and then 2, and then 1. Fundamental counting principle says multiply all those together. And what does that equal? I'm ashamed I don't remember that this is 40,320. In the next video, that'll make a little bit more sense. Why would you know the answer to 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1? Because that type of multiplication problem has a special name, which you're going to learn in the next video. So if we have 8 books and we want to put them on a shelf, there's 40,320 ways to do that. Now, what if 2 of the books were the same? Or what if 2 were the same and then 3 more were the same and the other 3 were all different? That's a trickier something to figure out, but not impossible. And when the time is right, we'll be able to figure out how to count both of those pretty easily. You'll see. The video is over, but at the end of the previous video, I was prepping and I was like, hey, I wonder if these people would like to see what I do first when I start prepping for the next video. So this won't take but just a second. But the first thing I have to do is get rid of everything. And the easiest way to do that is to do undo. And as a lot of you may know, in applications like Microsoft Word, Microsoft Excel, there's a keystroke for undo. It's Control-Z. So when I want to clean everything off to start the new video, I just hold down Control-Z and watch everything disappear. But I don't want to do it too far because I don't want to lose the first page. Oops, totally undid the first page. Let's Control-Y it back to the way it was. And, oh no. Oh, this was video 2. Okay. All right, y'all can stop watching this. I'm going to prep for video 3 now.